So let's define an automorphism. Automorphism is a group isomorphism phi from G to G itself, where, of course, G is a group. And, you know, I could even say this is an automorphism of G. Automorphism of G is a group isomorphism, phi from G to itself. So one of the most important examples of an automorphism is the conjugation map. So let's say, so if we're talking about conjugation by y of x would be y times x times y inverse. So let's say that y is in G, right? So this is the map that we would define as conjugation. And so we showed earlier that conjugation is a homomorphism. So remember, a group isomorphism is something that's a bijective map. So it's got to be, right, this means it's bijective. And it means it's a group morphism. So it's got to be bijective and it's got to be a morphism or homomorphism. Same difference. And so we showed that it's a morphism. So we can show that this is bijective, and what we can do is we can just show that one way of showing that something is a bijective map is to just construct the inverse function. So inverse of conjugation by y. So this will just be conjugation by y inverse, right? So conjugation by y inverse of x is going to be y inverse x, y inverse, which of course is just y. And, you know, so what will happen is if we first apply, so let's say we first apply conjugation by y, and then we apply conjugation by y inverse. Let's apply that to x. We'll get conjugation by y inverse of yx y inverse, right? And now we conjugate by y inverse. So we have y inverse times everything on the inside, yx, y inverse times y. And now we can just rearrange the parentheses, you know, and these will cancel by associativity, of course. So that's x. So conjugation, and of course y could have been any element in G. So conjugation is an example of an automorphism, and it turns out it's one of the most important examples.